fact, I'm not going to use it too much in the mold, because on the side of those eddies there is upwelling, and so we can see here the upwelling here and upwelling over there. Those are the cold wedges seen in the satellite observations. But more interestingly, what we did was calculate the vorticity on isopic null surfaces. So this isopic null surfaces, 23.8 gram per kilogram, lies between 50 and 100 meters. The spiciness is something that the oceanographers use to qualify water mass. It's a combination of temperature and salinity, which is high. Spiciness is high when the ocean is warm and salty. So we say it's spicy because it's warm and salty. And when it's cold and fresh, we say it's minty. So low value of spiciness. The spiciness is conserved on isopic null surfaces. So it's a conservative thing if there is no mixing. And in case of coarse mixing, then it is changed. So if you have a water mass with a specific spiciness that is moving somewhere, it should keep its spiciness unless it is mixed with another water mass. Okay? So on this plot, we show the spiciness on the surface in June 14, 1983. Okay? And we can see that the Great Whirl, so here is the Great Whirl and here is the Southern Gyre. We see the Great Whirl as maximum spiciness, high spiciness. So the Great Whirl is spicy water and the Southern Gyre is minty water. So that is very important for the interaction, because if they interact, we should see something in the spiciness. Okay? And then we look at the various parameters along that section, like velocity, relative vorticity, density, and things to characterize, see what's happening. So with using those things, we're looking at what is happening. So first thing we've seen, okay, rapidly, is first let's look at the cyclone flanking the Great Whirl or the Southern Gyre. So this is observation from satellite altimetry, where we have the Great Whirl over here, and we see several cyclones flanking it. And when you look, this is a 1/4 degree simulation, that's a 1/12 degree, and you can see that those filaments are cut very often and untrained by the Great Whirl, and they generate cyclones. And the same for on the Southern Gyres, they generate the cyclones. So in fact, the cyclones that we see are, just extracted from the filament of the boundary current. So the generation mechanism is related to the offshore shootings of those cyclonic vorticity filaments, which are which are strained within the boundary current and shot offshore. So that they're called bursts. So there are some theoretical and idealized small simulations studying those processes, and in fact the model reproduces those processes pretty well. So we didn't go too much deeply in this analysis, but the analysis of the cyclone is really the result of the instability within the boundary current, which is described elsewhere in a series of papers. So now we're going to look at the big thing: how those two big eddies, what happening? How do they interact? So we found several scenarios. So what we've been we're looking at what's happening, how they move. And what we found is the following. We have 3 scenarios. The first one, no interaction. The second one, there is a collision between the two, but they don't merge. And the third one, there is a collision and they totally or partially merge. Okay? And in all my simulation I had, I found that no interaction, one is gives 0, one gives 3, 1, 1. I just look at 10 years, this one. This one I looked at 32 more years. But, so this one seems an outlier because dominant response is no interaction, but all the others, they say no interaction is rarely happens. Okay?
What is your cause here? S41, S12, what does it mean?
are these things. Okay, S is simulation and A is analysis. Okay, so those are no data simulation. This one is with data simulation. 4 is 1/4 degree, 12 is 1/12 degree, and this is the first simulation, and this is simulation 1, 2, and 3. Okay? Okay, and they refer to the table I showed at the beginning, which you don't remember, obviously, because it's. But in the paper, you can go back to the table.
No, what you say, all alike, one is very different. Which one? I mean, the last one is 2377.
Yes, okay.
Characterize what this is.
So that one is the UBS momentum advection speed. Okay? So, in fact, I did in my first paper, I did the work with this. Okay? And I published a paper with that. But I was saying that, okay, the conclusion of the paper said the model may favor a scenario. For numerical reason, we need to dig more. Okay, then I started to dig, looking at what is data simulation doing. Didn't change much things, but then I changed the advection scheme and it's changing things. Okay, but don't let me tell you my conclusion before I get to it.
That applies change momentum scheme for advection of momentum.
Or momentum.
Of momentum. Tracers.
No, momentum. Okay. Yeah. And I think it has some. It's not. I'm not surprised for some, but I will explain. That will be my conclusion. So, let me see. So you see, the Southern Gyre is growing, but it stays in place. Doesn't move much to, doesn't go beyond 5 north. So the Great Whirl, is spinning up, generates cyclone, interact with them, and so if you look at spiciness, you see this. So I'm looking at spiciness in this box. Okay, this box is about 4,000 grid points. Okay, so because we'll do some statistics on it. Okay, so looking at spiciness, you see the Great Whirl has high spiciness, and at the end of the monsoon cycle, the high spiciness is still over there. There has been some intrusion through the boundary current of waters of lower spiciness, but still it remains high spiciness, and the minty waters from the Southern Gyre are still in place. Okay, they didn't change. So no interaction.
No, I'm sorry. Just a question. Did you calculate the spectra of kinetic energy for this and another cases?
No, we didn't do any spectral analysis for this one. So, to summarize here, this scenario is seen is 4 among 5 simulations, only one doesn't have it. It's not frequent in 4 of them, and it's quite frequent in another one. It's dominant in 1 of them. And at a large scale, this reproduces slowly varying circulation with the small cyclones being the eddy variability. And you can see that there is some kind of a socotroidy that are appeared over here. Okay, and in what I call the GW, the Great Whirl box, so at mesoscale, the burst of vorticity and small cyclone mix a little bit of spiciness over here, but in the GW box, the spiciness remains high. So now we go to the second scenario, so which is described over here with the vorticity and the velocities. The Southern Gyre extend to the north, collide with the Great Whirl, but between the two, it builds a very strong filament of positive vorticity. So this Great Whirl is pushing the other one, which gets contracted and moves toward the Socotra Island to eventually form an eddy, which can be called the Socotra eddy. And if you look at spiciness, in this box, so the spiciness is very high. When it moves in, you see that in low spiciness begin to intrude and high spiciness remain there, but they don't mix. There is no spiciness mixing, and these things comes in and fill up the box. So it's very clear that we'll also look at see surface temperature, but it's very clear that this feature is moving and taking place the other one. It doesn't mix with it. And the other one is shifted. You see high spiciness over there. It has been shifted. So one process to generate the so-called eddy could be that the Great Whirl is pushed in a different position. Okay, so and if we look at the cold wedges, you have one here north of the Great Whirl and one here north of the Southern Gyre. We can see that the two wedges are merging to end up with one cold wedge. And, but the two eddies didn't merge. And the papers looking at satellite observation, seeing the merging of the cold wedges, concluded that the two eddies had merged. So in fact, merging the collision, the cold wedge doesn't mean merging the two cold wedges doesn't mean that the two eddies have merged. They could interact without merging, and still you will end up with only one cold wedge.
To comprehend, this is all done by the same method, which is called EDDIES, and vertically it's time, right? With
yeah, we have the same things in the quarter degree model too. Yeah, this is done with the same model.
It's 12. It's 1/12.
Yeah, it's 1/12. Huh? Yeah. The result I'm showing you are 1/12. So another view of it is along this, the section, the section that goes this way and crosses two things. So there are plenty of things on those sections. I just, I don't know which one we should, but let's look at the vorticity, which is the green line. Okay. So the black line are density. Okay. So this anticyclone density lines are deepening, and moving back. So the Southern Gyre is this ball, the Great Whirl is that ball, and between the two you have positive vorticity and negative vorticity within the anticyclone. Okay, and a positive, which is the red thing around the red filament around the end. Okay, and as time goes by, which is I think 14 July, August 3. Okay, this way, top. Okay. We see that the Great Whirl, which is pretty wide, is shrinking. It's pushed by the Southern Gyre, which is pushing it, and we can see that the positive vorticity separating it are increasing, and it's increasing quite a lot. It's over here, and now it's here. So the two eddies cannot merge because they should break this filament of vorticity to merge, and they cannot. This is really a shield that is built between the two eddies, so the two eddies cannot interact, and they're just pushing each other. So there's this front, density front and vorticity front. They shield the eddies and prevent the merging. So that's a process that prevents the eddies to merge. So what we did is we took that box and we did a PDF, of the spiciness. Look at the distribution of the spiciness in this box over 10 years of an experiment. We calculated the PDF of about 200 bins of small values. Values range over 4 to 7. Okay, and over 10 years, if you look at the whole distribution, I get 4 peaks. It's not a Gaussian thing. It's just I got 4 peaks. And then I plotted the distribution for every 5 days for the 10 years. Okay, and I outline in green the years where I do not have the year where I have a merging of the eddies, and the year where scenario 1 where there are no interaction between the two, and in blue where there are collision with no merging. Okay, and this is a line in spiciness that separates the two cases, which I took from here. Okay, and if I want to identify the peaks on this, okay, scenario 1 is this one, 2, the second peak corresponds to that, the third one, and the fourth one is just an anomaly in 2006. That peak could have merged on this one, this is an anomaly. But, okay. So we can see that when we have no interaction between the eddies, we don't have low spiciness values in this box. Okay, so the spiciness is a very good tracer of the interaction. And in fact, what you can do, we can make composite of those distribution. And so we make a composite in May, June, July, before the collision happened. The collision happened at the end of July. And August, September, October, after the collision. So the composite of no collision year is the red one. And the composite of the collision year is the blue one. So before the collision, they are very much alike. Okay, so spiciness is distributed very similarly within the GW box. But August, September, October, after the collision, we can see that when there is no collision here, the spiciness conserves its large values. But when there is collision, then the distribution is completely shifted toward the smaller values. Okay, so the change of spiciness is one way to identify if the water if merging occur or not. So that could be an interesting way if you could look at Argo floats, for example, which goes into this region to see how spiciness evolved in observation. They could tell us, oh, that this year was a collision year, this year it was not. Okay. The third scenario is I call it 2B because it is a collision, but there is a large partial and sometimes total merging. So the two eddies collide, but there is a little shield between the two. The shield is not very strong, and therefore they mix together. And you can see that on the spiciness. You know, here you have the Great Whirl, here you have the Southern Gyre, so minty and spicy water, and you see that they are looping around and mixing all together. So here we do have a mixing of the two eddies in this scenario. Okay. Interestingly, if I'm looking at this collision with fusion, I said, oh, this is in French, but it is interesting to see that it happens, the collision with fusion here, in this experiment here, which has a partial seed boundary condition. Without too much changes. So, because we always wonder, the boundary condition here will certainly have an impact on the dynamics in the way you resolve the dynamics. So that's why we tested the slip and partial slip boundary condition, and we didn't find, well, between the 112 degree, the one that has the greatest occurrence between the three runs, the greatest occurrence of merging is the one with partial slip. The others are 0 and 1. That one is a different story. I'll come back to it in my conclusion. So this is just to show that this is operational analysis. So it's a model with data assimilation. They are simulated in situ observation, satellite observation, and so on. And it was just to show that how the merging occur in this model. So the analysis also showed that the scenario can happen when you do data assimilation. So let's discuss those results because they're a little bit puzzling. So to summarize quickly, I mainly focus the discussion on the collision between the Southern Gyre and the Great Whirl. Okay? So the possibility of the merging of the Southern Gyre with the Great Whirl has been reported in observation-based study, based on satellites, essentially. And based on the fact that the cold wedges were merging, but we know that the collision without merging, it has not really been reported in other observations, okay? In the way it is described over here. So the question is, when you do a model simulation and that you have no observation to check it, you scratch your head and you say, okay, you better think about the model solution. So could the model, due to numerics or configuration or some reason which we haven't spotted, favor the scenario of the collision without merging rather than the other one? So we have to ask this question and try to answer it. The second is, is a present observational network suited to observe this rapid collision event. It's really a rapid thing, and we may not have the proper observation. So we have to question the model, but we also have to question the observation. So what we did to answer those two things is we resampled the 112-degree simulation in the same way as the satellite observation, AVISO, okay, which is 1/3 degree, 7-day mean over the period 93-2004, 12 years, okay, and we compare the model with the AVISO, sea surface elevation, and the Laplacian of the sea surface 8 as a proxy for the relative vorticity. So in that way, we may have a fair comparison between the model and the satellite observation. So we did this, and this is the result. So on this side here, you have the model sea surface elevation for a period going from July, August, and okay, July and August. And this is another series from the AVISO, not in the same year and not exactly the same period, but we pick up a series that resemble very much in terms of pattern. Okay? So what we see is the model will have, you know, I can identify the Great Whirl. In the model, it's very easy to know where is the Great Whirl because we have plenty of information, vorticity, we have high resolution, we have the 112-degree solution to pick to make it. Okay? And this is the Great Whirl and the Southern Gyre, and we have an eddy here. So here, I would say that if I have to comment the observation, the satellite observation, that the Great Whirl would be here, and the Southern Gyre would be here, and here we would have a cyclone here. And the evolution would be this way, you know, I know this one, you know, the Great Whirl is being pushed by the Southern Gyre, pushed here, and at the end, I have the Southern Gyre took the place, and the Great Whirl is here. I know this scenario because I have a spiciness, I have everything to know that this is a scenario in the model. And you can see that those patterns, we could very well just by those patterns say the same scenario occurs as in the model. So the observation, the model is able to reproduce something here, the observation. Then I am looking at the vorticity, okay? But the proxy of vorticity, you don't get exactly the vorticity from satellite observation. You take the Laplacian of the sea surface 8, and you get a proxy of the vorticity, okay? Which is plotted here. So here is the Laplacian of the filtered SSH, that 1/3 degree, just like the AVISO one, in the model. And we do identify very well the Great Whirl and the Southern Gyre, and over here, and we see that the Southern Gyre is taking the place, and the Great Whirl is pushed on this one. So this sampling, with such a sampling, we should be able to find, you know, we're able to still to follow the same scenario. When we look at what happens in those things, what we mainly see is the interpolation radius for the analysis, objective analysis performed to fill up the gaps in this map. And we cannot identify clearly where is the Southern Gyre, where is the Great Whirl. So I could say, well, maybe it's here, but it could be somewhere else. And I cannot really conclude from the observation because what is the dominant pattern is the radius of used for the objective analysis. Because the satellite, you know, is measuring only on tracks this way. So to produce that map, you have to do some kind of objective analysis, which is performed by AVISO. Okay, so the conclusion is we cannot conclude if the model is wrong with the observation. The model could eventually reproduce a scenario, but cannot conclude this one. So now let's go to numerical. So we've seen observation. Let's go to the numerical consideration. So we have. I took again, you know, 1, 2, 3, 5 simulation version of NUMO. So I outlined this thing. If I take those 3 simulations, okay, and the analysis from operational center, okay, here, okay, I can see that they are all more or less consistent. They say collision without fusion is the most likely scenario. They all agree, you know. so they are consistent, and what we can say is that the model free run are consistent with the model with data assimilation. Okay, but we know that at those low latitudes, the altimetric signal is not directly connected to ocean currents, because the connection is through geostrophy, and geostrophy is pretty weak at the equator because the Coriolis parameter is very weak. So data assimilation of sea surface elevation doesn't constrain well the current at those low latitudes. So it could just be that this, because it's not well constrained, it just provides a solution which is close to the run without data assimilation in this region, because the data assimilation is not efficient there. And because it's the same code and the same model, it provides similar solution. So there is some consistency over there. So we can say that all those experiments are basically the same, and they provide a scenario. And okay, so now let's get to the last one. Now, if I look at this one, well, in fact, I'm looking at those two. I'm looking at this one with a partial slip boundary condition, and I'm looking at this one with a UBS advection. So different advection scheme on momentum, and that one, you know, tells me that the most likely scenario is no interaction, and that the other scenarios are reasonably probable, okay, 7%, but certainly not dominant, okay? This one, with a partial slip boundary condition, tells me that it found 3 occurrences, much larger number of occurrences over 10 years, you know, than the others where there were no interaction between the two gyres, okay? So there could be a dependency upon lateral friction, because this scheme has the boundary condition, the sidewall boundary condition for that scheme is a little bit like a partial slip boundary condition. So maybe it's an advection scheme, but maybe it's a way the boundary condition in the advection scheme is treated in that model that provides these results. Okay? So the next step would be to look at other models.
But Bernard, could you explain? You see that 23 is a big number, means that you're counting events.
Yeah, but
number of
I look at only the last 10 years of those models.
Yes,
so there is a bias that you have to consider in looking at. If I would take only 10 years, I don't know. But
why this one has more events total? Because 23 plus 7 plus 7 is 37, and it is very much more than any other if you add them up.
Well, the other runs are, you know, I first did this work, and I added this one. Those runs are longer, so they are 30 years, but I just look at the last 10 years for this paper. So I didn't go back to, but this will not change. I think this difference is really, if I do 30 years, I will get the same proportion in those ones.
Because you look at, you have more tries, right?
Yeah.
I mean, should I normalize these figures to be, so that they should adapt to something the same, and how should I do it? Because, again, you have more events total.
Yeah, in total I have more events. But the more events don't help me to converge to an answer. In fact, if I had stopped there, I would still be convinced that if we go with a ship, we have very good chances to find a collision without merging. But now, I'm not convinced anymore. And one thing I wanted to do, I asked the guys in Florida State to look at this in ICON to see what other models do. And I would like to have results from a sigma coordinate model.
No, but you see that.
Because I think if I start, if I put other model than NEMO, I may still have different things in there.
That's probably the contribution to confusion.
So let me go to my conclusion, then we start question and discussion. So, conclusion. 110 realization of a seasonal interaction between those two eddies. So I don't think any oceanographers, even models, even perform such kind of studies. You know, like I'm studying something and I do 100 simulation. We're just beginning to do ensemble in oceanography, while its meteorology has been done much. Okay, and this is not a clean ensemble. Okay, so that's why I'm not. If you go back through my slides, I never talk about ensemble because ensemble in mathematics and statistics has a bit different meanings. Not that because you have many realization that you have an ensemble. It's a bit different. So, but I have 110 realization of a process provided by 5 different global leading simulation. I should have had with the same numerical model. That's an important thing. So the origin of the cyclonic eddy is flanking the Great Whirl. You know, bursts of positive vorticity from the western Barnier current that collapse into coherent cyclones. This is a common result that all models do, and I think the model is fine on this process. So we provided an answer because of the paper of Bill in 2013. They were asking what is the generating process. They noticed those from satellite observation. They didn't know about the process. So this study provided a scenario for the process. Then, more complicated, the interaction between these two big patterns. We have 3 scenarios: no interaction, collision without merging, and partial merging between the okay, with different robustness and things like this. So what the last point is, well, the Socotrali is a side. It's just when the Great Whirl is pushed after the collision without merging. That could be one process, but it's not a unique formation process because sometimes it exists when there is no collision between the two. So the Socotrali could have different origin depending on the year, and so different properties in spiciness. So the perspective, I think we need input from other models to go forward, because we have NEMO with its own numerics, with its advection scheme, with the other thing, with the way it treats bottom topography, and it would be interesting to see how the MIT JCM, especially if they use the Géosciences topography and ICOM, perform on this. Things. Then we could eventually also approach, it would be interesting to approach with a real doing ensemble and not only a realization, which may not be all independent things, so a clean ensemble. Of course, we should try to go in more in depth using Argo and historical observation to perform spiciness analysis in this box to see if we find this type of peaks. Because if we find the similar peaks in the observation, you know, we don't care about to have a long time series. You know, we could gather all the information of this area, make a distribution of spiciness, and see what we have. And if we produce the peaks, I think that will be very convincing regarding the fact that the Southern Gyre can really push the process of the collision with the merging could happen. You know, that of course, if we have a very Gaussian distribution and things very clean, then it will be proved that the model is wrong in this scenario. Okay. Of course, we can explore the robustness to a broader set of numerical and physical parameters within NEMO, but all that requires, of course, a lot of computer time, because one thing I didn't say, that if you run a regional model, then the Southern Gyre doesn't move. You need to have the whole Indian Ocean basin to have the viability of the Southern Gyre, because its viability is driven by some kind of a integration of the curve over the whole basin. So you do need just a regional model is not enough to study that problem, and therefore the computer cost is big because you need to run a large-scale model. Okay, thank you.
Thank you very much. Any questions, please?
I have something really silly, but can you explain how you get those numbers in the tables that the man is interested in? Are you going through manually saying, here you have a collision and merger, here
Yeah, that's what I did. I spent hours in front of my computer screen, yes.
Okay, so it's a manual process.
Yeah, yeah. There are all the processes, but I think spiciness is. You look at spiciness in it's a movie of spiciness. It's clear, you know, when you see if a spiciness mixes or not. Okay, because if I go back to this plot, it's very artisanal way. Okay.
But you see, what you get here, you see.
Это вопрос или выступление?
Это вопрос.
Ну, тогда подождите ответ сначала.
Okay. You see, Josh, when you look, you see how things evolve, and you have your box. When you fill up your box with that, you know that you have a collision without merging.
So you have a script that produces all these plots per what time step over what period of time?
Yeah.
Because I think the question is about...
I have every 5 days. I have every 5 days.
Every 5 days.
And I have some of them I have every day, but yeah, it's very fastidious. Yeah. I agree. It's an old way, old-fashioned. I'm not old-fashioned.
My question is, what's the thickness of these gyres? Because underlying Red Sea high salinity water may influence also on spiciness.
It could, yeah, it could. We can see here. Okay, this is 200 meters. You can see that the deepening of the isopycnol relative to the Great Whirl, so 300, 350 meters. So they really remain above this.
300-400 meters only.
Yeah. And we look at the spiciness on the isopycnol, which is spread. It's a 23.8, which is around here, which is between 50 and 100 meters.
Because Red Sea water 27.2, 27.3, something like that.
Something like that. Yeah, it would be a little. Yeah, it would be in this range.
Any questions?
How strong does bottom topography influence on the structure of Great Whirl or Somali Current?
The geometry you have is, so you have a coastline. So on the model, and you have a constraint coming from the Socotra Island when you have a strait, you know, and so that. Okay. So here there is not much, you have a coastline, so the current flows along the coastline. So of course the shape of the break will trigger, the vorticity shear and may play on the instability of the current and will probably influence the burst of this of the cyclonic vorticity to the Shirshov cyclone. But what you have here is you kind of a blocking of the topography because you have the Socotra Island over here with a small passage, and so the Great Whirl is constrained by the topography very much in here, and that's why it's not bumping so the constraint from the north is important, yes. And sometimes, in fact, this is pushed through the another large eddy in this region sometimes. Paulina.
Now, you see, please, why does the front between two gyres disappears in the scenario 3?
Well, I don't know. It is. I think I didn't look in detail. I look at the scenario. The thing is the filament, the vorticity filament that separates the two is weak at the origin. So then the merging is possible. It's not that it disappears. It is weak. If we look at the scenario from the reanalysis, which is this one, I think. Yeah. At this time, you have very strong separation of vorticity. But for some reason, this one has been broken. It can be broken, by a cyclone coming there, and because the cyclones sometimes they go wrong, and they merge again into the boundary current. So a cyclone can cut this filament. That's things that could happen. So, and then here you can see that there's basically no more red between the two. So it's very favorable for the merging. But if this filament would not be cut here, so sometimes it's just a stretching of the things that, because those filaments are stretching. So if the eddies are moving and the large eddies are moving, they can stretch the cyclonic very thin, and then it weakens. But I didn't look at this in real detail, I must say. It is an interesting issue. Why, in some cases, this filament, this thing is weaker, we could look at it.
Does it mean that the front is not formed from the, like a gradient between features of two gyres, but with another water mass coming from the boundary current?
I think
this
the gradient
is not front in the sense of
well, no, it's not a front in, okay. I don't think it's a front in terms of, it's a density front, but it's not, it's formed by advection, I think, and instability is coming from the boundary current, which are shooting offshore, mainly. So it is, and the instability process leading to this shooting is some kind of a viscous process. It is described in a couple of papers.
It should be also very much affected with sleep or free sleep.
Yes, I think it is. There is some sensitivity to the sleep and no sleep.
Maybe not so simple.
But the idealized simulation that were done on this instability process, they look at the various viscous boundary layers in the boundary there. They're using some kind of a straight line topography, vertical wall, so they are very idealized condition. I think this problem is still sensitive, and that's why I've said dispersion in the stable is still sensitive to details in the numerical parameters that we're using. So. I published a paper, but now I think the conclusion of the paper was I need to go deeper, and going deeper, it's more, at the moment it's more puzzling than reassuring, so I need to do something else.
But you mentioned that EDDIES you say is coupled with new computational kernel of your model. What do you describe? Because can you switch off, like make central advection, like fundamental for the new model 4.0 alpha and see what happens?
Yeah, cool.
Because you highlight only one feature in your code, which is different from previous, but actually there are more.
I agree. Yeah, of course. Yeah. There is a vertical resolution. Some are 46 levels, some are 75 levels. There is a forcing field. That's why I say I need a proper ensemble.
No, but you see,
I mean,
because what puzzles in anti-stock in general is that you highlight that, okay, your model which has UBS advection for momentum, which is very different from everything else than previous.
Yeah.
And
but
but that's also different because I presume that 4.0 alpha needs new generation of NEMO curve, that new time stepping and everything becomes else, right? What time stepping?
Yeah, well, this is alpha. It's not even the beta version. Okay.
It's not a big changes in NEMO.
No,
but it's not big change.
But you see, to begin with, NEMO using leapfrog time step.
Well, this is a leapfrog. Still, yeah.
That is incompatible with upstream bias scheme. It's unconditionally unstable. You cannot do it unless you do something very artificial and...
Well, which is probably what's done, but okay. Yeah. No, I fully agree. The thing is, what I did, I gathered simulations that were done for different purposes and look at that problem. And I think now that I have all those results, and I think that's the way research proceeds usually, now that you get your result, now I say, if I want to answer this question, I need to have multi-model, multi-ensemble approach if I want to really to clarify this kind of thing. And that makes things much more complicated. But I think that's what I need, okay? Because taking simulation that were done for different purposes, you know, some were made to test if we make progress with things with, you know, sanctified level, what happens with ants. So there were different things. They were all long simulation, all 30 years, okay? But with different aims. And so, but then that makes a lot of simulation available and interesting result to look at. So you say, okay, I have a model and then I have a scientific question, so I try to answer it. In fact, that's why I emphasize this issue. If I give a seminar at Shirshov only, I will not too much emphasize this numerical issues because I think it's a good place for doing it here. Okay, that's why you know, I emphasize the things because at least I know that one here will understand what we're talking about. Okay, doing modeling is not an easy task. If you because there are so many parameters that you have to take into account, and the ensemble approach and the multimodal approach is probably a good one in many cases, but it's a one that is very heavy to carry.
Especially frictions and these and both.
Any question, please?
My question is about the relative velocity, vorticity, I'm sorry. You compared the relative vorticity from the model calculated on the basis of the velocity field, as well as with the satellite vorticity calculated as a Laplacian from the C surface height.
Yeah, for the model, I also do the Laplacian for the comparison. When I do the comparison, I take the model C surface elevation and I calculate the Laplacian of the model C surface elevation to be comparable. I didn't use the vorticity calculated from the velocity field for the comparison.
My question is, did you calculate in your model the C surface height directly or not?
Yeah, the C surface height is a prognostic variable, so it is calculated with the time stepping and the same way. So it's calculated from the model. The difference between the two is that the satellite picture, I can go back to this one. Okay. So this is obtained by, you know, satellite tracks. They get, you know, this passing, and then they do an interpolation. Okay, and the interpolation they use a window of 7 days and some radius of the correlation radius. So they provide 7-day maps with every 1/3 degree resolution. So what I did for this model, I took my model C surface 8 and I sampled it on the 1/3 degree resolution to have the same resolution and average it over a 7-day period. But this average is done from every model point and not from the track. I didn't simulate the tracks first. So there is some differences in the two. And that's probably partly what explains this, why with this I can still identify, even with the Laplacian, some kind of patterns. But if I had done the same and performed the analysis with the same radius of deformation, for the interpolation, I mean, I would probably get something like that from this one. Okay? Yeah.
Thank you. But you see, you compare it here, because you compare it here, that's here 1999 versus 2004, which means that you cannot really compare.
Yeah, but
directly you probably.
I don't have any data simulation here. I'm just looking for analog situation and see if analog situation, one which I know everything. I have a scenario, and with this analog, I cannot construct the same scenario. And the conclusion is, the reason is because the processing of the data is not adequate. That's the only thing I'm saying. And so my conclusion is I cannot use that to invalidate or validate my model. Okay, I'm not, you know, I don't care if observation invalidate my model or validate the scenario or invalidate it. It's fine. I want to know what, you know, if the model it fits the observation or not. But there, I cannot use, this cannot be used. So I cannot conclude if my model is doing it correct.
Any questions, please? Thank you. Thank you once more.
Сергей Анатольевич может сказать сейчас, да?
Ну, я не знаю, по-моему, хороший доклад, а что мы можем сказать? Thank you once more. Very interesting realization of your model concerning this very rare visited place, yeah, especially with pirates now, yeah. Only modeling, only EDDIES program, and so on and so forth. But nevertheless, for me, for example, very interesting new term, spiciness.
Yes.
Because as a specialist in water mass analysis, we never use such term.
The first time
But maybe we will start, because from this point of view, Atlantic Ocean is spicy, Pacific Ocean is minty. Yeah. This difference caused Great Ocean conveyor belt, for example. And some collections are very interesting also because we have different realization of models with different advection schemes, for example, and different results. And we even don't know is this scheme is the most important for different results, your last row or not, for example. So for us it's very interesting because our modeling, ocean modeling is a little bit lower. Well, where is our models? It's very interesting for young sciences also, not only in oceanographers, but also climatologists, meteorologists also. And of course for our numerical mathematicians. So thank you once more. Maybe somebody wants to say something else. No? Thank you.
Maybe only from just not question, but one thing. I hope, Bernard, that it is not last report, not last lecture on our seminar. I hope that in the future you will give us another
Next year,
very interesting lecture about studies which you have done here inside in the frame of your background where you are leading scientist.
We have much more interesting places in the ocean. For example, Agulhas Current.
Yeah, they are
very interesting one.
Yeah.
Same problems. Maybe others. Direct passage. Up to you. You have broad interests also.
I'll try to surprise you again. Thank you very much. Thank you. You're welcome.
Just about my question about spectra, because you got very interesting results about structures, and it is very interesting to understand these very structures are flowing. This is important numerical model, but maybe some theoretic will be very useful. And this
водной массы, но физический смысл, почему
Some is Geosciences cascade, Oceanology cascade. We developed some diagnostic studies. I really need the turbulence approach to look at those questions. Could be very competitive.
Lowest key.
Here, so here we got in fact what we found is
То есть дело в том, что число достаточно простая.
we found that the slope is changing with the season because we get different temperatures in winter time where we have winter significantly. But it's very significant, and especially on the vorticity. But amazingly, not on temperature. Which means that the turbulence seems not to be transported. So we look at the vorticity is some change in the velocity, but not on the temperature. Which means that you think that this more turbulence has no effect on transport. We're just beginning to mention that. That's last year, a colleague of mine, Julien, visited, but he will come back next year and it's very special to work on this. This is many, we'll probably come back next year. That's our last one. Okay. Okay.
У меня сейчас очень тяжелый период настал. Экспертизы,
So you are working
по аудиторам, те самые отчеты.
What's your topic for research?
Поэтому надо сейчас стараться через затягивать. Я послал людей, через перспективу, значит, мы так и оставляем. И белые сейчас тоже уже и смету. Я взял прошлую смету, единственное, я уменьшил на командировки, вместо 850, 700, даже абсолютно не важно, 750, но добавил, значит, сотню, да, зарплату, да, что пережоги на него все нормального контракта. Значит, командировки надо, тоже здесь не важно сказать, ну вот я писал там еду 3 человек, надо еще какие-то командировки, положено, значит, положено. Командировки. Московскую не надо, потому что Богомолов нельзя командировать. А больше такого, только своих это нонсенс. И оборудование. Значит, вот вы все это пишите, ну еще что-то такое.
Ну да, именно сейчас приехал, и сейчас спрашиваю.
То есть сейчас нам нельзя никак не подтягивать, потому что хочется с этим делом развязать, чтобы быстрее.
Хорошо, сейчас форсируем тогда. Я сейчас значит, у нас получается оборудование командировки и перевод на английский язык. Нет, еще видео должно подготовить.
Она мне, если бы она мне завтра прислала вот этот текст, я бы занялся этими вещами. Ну ладно, вам всех погостить.
I think everything lies in the impact.
Ну, в общем, да, нам надо, конечно, сейчас очень так, к сожалению. получается, в декабре месяц очень
It
картина.
tries to show some blockages. One thing I don't, one thing I still don't know is why.
Писать нужно. Ты меня спросил, Дарья Юрьевна вас же просила,
Southern Gyre
вот,
is
выше не просила.
Sometimes looks like
Наверное, может быть, не просил ее, я написал отзыв на гидрографические наши справки. Ну, хороший пойти.
Больше не делайте.
Да?
Я не пишу.
Нет, я написал, получается, ну, то есть, а я был уверен, я просто вышел и сказал, что я вас просил.
Нет, ничего такого не было. Даже не подходил.
Я тут
Пишу, конечно, но на будущее так не пошло еще работал в как раз справа, подписывали ну и все просто тем более, если я читал, вообще не подойдет.
Ну тогда давайте подождем, мы могли это в 3 фразы.
Не, ну зачем?
Ну хорошо,
Я совсем не подойду. Все это дело. Я пишу, но больше так не надо.
хорошо. Так, вот здесь.
Я ее видел на общем собрании, когда я видел на общем собрании, но там не нашло. Все, договорились, да?
Да, хорошо.
А так я всегда не подписываюсь. То есть я могу попросить, чтобы написали, а мне нужно прочитать. Написали, я буду квалифицировать.
Ясно.
Так, отлично.
Понятно. Хорошо. Я понял.
Well, I think well, I tend to believe that the EDDIES solution is a good one. Okay? That's my intuition. My intuition is so thank you, and well, maybe I'm going back home tomorrow.
Okay.
That was my last day, so I'll be back in a few months.
Так, ну, а сейчас, секундочку, особенно тут помогать мне.